Is the transverse wave theory for light actually correct? The transverse wave theory of light is generally credited to an English doctor and scientist named Thomas Young. However, to understand this theory, it is best to understand a little about the history of light on planet Earth. Throughout the last few centuries, humans have debated the nature of light, and two main scientific theories have arisen as popular favorites. One of those theories is the wave or undulatory theory for light, where light is thought to be a motion through a material medium, like sound is a motion through a material medium of air or water molecules. The other one of those theories is the corpuscular or particle theory of light, in which light is thought to be made of individual particles that move through any medium. For example, like a tennis ball moves through the medium of air or water molecules. It's important to explain a little background of how these theories arose and a little bit of the history that surrounds the view of light by humans throughout the past. One of the earliest theories of light is from a Roman philosopher and poet named Lucretius, who, even before the development of the religions of Christianity and Islam in 56 BC, clearly describes the theory that light is made of atoms that move very fast. Fast forward to the year 1228, when the first president of Oxford University, Robert Grosseteste, theorized that all matter is made of light. But not until the 1600s would more detailed theories of light arise. The French philosopher René Descartes really helped us out. Descartes was one of the first people to theorize publicly about the nature of light, and in 1637 he published his work named Discours de la méthode, translated to English, Discourse on the Method, in which Descartes describes both a wave theory of light and a corpuscular theory. In Discourse, Descartes is the first to try to explain the phenomenon of refraction, how light appears to bend when going from one medium to another, for example when light passes from air into water. Descartes compares light to a tennis ball that changes direction when colliding with water, and this is a basic description of what has come to be called the corpuscular theory of light. The theory that light is made of material spheres or atoms that move through space like a ball moves through air. Descartes writes, translated from French, "Consider that the bodies which can thus be met by a ball passing through the air are either soft or hard or liquid, and that if they are soft, they completely stop the ball and break its movement, as when it is thrown into linen sheets or sand or mud. Whereas, if they are hard, they deflect it in another direction without stopping it, and they do so in many different ways. And the same is true if we assume this body to be very thin, such as a paper or a linen sheet, so that the light passes through it. Finally, consider that the rays are also deflected in the same way that has been mentioned in the case of a ball, when they obliquely encounter the surface of a transparent body, through which they penetrate more easily or less than through that from whence they come, and this method of being deflected is called in them refraction." Descartes goes on to write, "Now let us consider that the ball coming from A toward D encounters at point B no longer a cloth but water, of which the surface, CBE, takes from it exactly half of its speed as did the cloth, and the rest being assumed as before, I say that this ball must pass from B in a straight line not toward D, but toward I. For, first of all, it is certain that the surface of the water must deflect it toward there in the same way as did the cloth, seeing that it takes from the ball the same amount of its force, and that it is opposed to it in the same direction." And comparing this to a ball with more velocity, Descartes writes, "But let us make yet another assumption here, and consider that the ball, having been first of all impelled from A toward B, is impelled again, once it is at point B, by the racket CBE, which augments the force of its movement by, for instance, 1/3, so that afterwards it can make as much headway in 2 moments as it previously made in 3. Now we can say that since the ball which comes from A in a straight line to B changes its direction at point B and takes its course from there toward I, this signifies that the force with which it enters into the body is to that which it leaves the body, ACBE, as the distance between AC and HB is to between HB and FI, that is to say, as the line CB is to BE. Finally, inasmuch as the action of light follows in this respect the same laws as the movement of the ball, it is necessary to say that when its rays pass obliquely from one transparent body to another which receives them more or less easily than the first, they are deflected in such a manner that they are always less inclined to the surface of these bodies on the side of the one that receives them most easily than on the side of the other, and this exactly in proportion to the ease with which the one rather than the other receives them. In this same work, Descartes also describes a wave theory for light, where light is thought to be a motion that moves through a material medium. Descartes writes, "But perhaps in doing these experiments you will be astonished to find that the rays of light are more sharply inclined to the air than in the water, on the surfaces where their refraction occurs, and still more so in water than in glass, quite the opposite of a ball which is inclined more sharply in the water than in the air, and which cannot pass through glass at all. However, you will cease to find this strange if you recall the nature that I attributed to light, when I said that it was nothing else but a certain movement or an action, received in a very subtle material that fills the pores of other bodies. And you should consider that, as a ball loses much more of its agitation in falling against a soft body than against one that is hard, and as it rolls less easily on a carpet than on a totally smooth table, so the action of this subtle material can be much more impeded by the particles of air, which, being soft and badly joined, do not offer it very much resistance, than by those of water, which offer it much more, and still more by those of water than by those of glass or of crystal. So that the harder and firmer are the small particles of a transparent body, the more easily do they allow the light to pass, for this light does not have to drive any of them out of their places, as a ball must expel those of water in order to find passage among them." I would say that, in general, as revealed in a work, Le Monde, written between 1629 and 1633, but only published in 1664 after Descartes' death, that Descartes primarily supported a wave theory for light, but also allowed for the possibility of a corpuscular theory. In his work Le Monde, The World, Descartes writes, "As for reflection and refraction, I have already explained them sufficiently elsewhere. Nevertheless, because I then used the example of the motion of a ball instead of speaking of rays of light, in order by this means to render my discourse more intelligible, it still remains for me here to have you consider that the action, or the inclination to move, that is transmitted from one place to another by means of several bodies that touch one another, and that continuously fill all the space between the places, follows exactly the same path along which the same action could cause the first of those bodies to move if the others were not in its way. The only difference is that it requires time for that body to move, whereas the action that is in it can, through the intermediary of those touching it, extend to all sorts of distances in an instant. Whence it follows that, just as a ball is reflected when it strikes against the wall of a tennis court, and undergoes refraction when it enters or leaves a body of water obliquely, so too, when the rays of light meet a body that does not permit them to pass beyond, they must be reflected. And when they enter obliquely some place through which they can extend more or less easily than they can through that from which they are coming, they must also be diverted and undergo refraction at the point of that change." The wave theory Descartes envisioned is called a longitudinal, or sometimes a point wave, and is the same kind of wave that sound has in air, where molecules of air collide with each other to pass the motion over a distance. In this kind of wave, there is no sideways amplitude of these waves, only a forward-back amplitude that represents the strength of a sound. In this view, light is viewed as a motion, like sound, that causes particles in a medium to collide with each other. You can visualize a field of little spheres, and in this view, light would be a chain reaction motion, where a motion causes one row of spheres to collide with another row, which then collides with another row, and in this way the motion which is light is passed on through space. A year after Le Monde, in 1665, in England, Robert Hooke also publishes support for a wave theory for light, which he characterized, like Descartes had, as a motion that is passed through a medium, Hooke identifying the medium for light as an ether, which is made of tangible particles smaller than atoms. The word and concept ether descends from pre-Christian Greek philosophers. University of Athens professor Evstratios Theodosio writes, "It is clear that, while the Greek philosophers from Ionia, Asia Minor, considered only 4 elements or 4 substances, i.e. earth, water, fire, and air, Aristotle himself adds ether. Ether will then be the 5th element, namely the quintessence. According to Aristotle, this element shows particular properties, as it is unborn, ageless, imperishable, unchangeable, and unable to grow or to deteriorate. Furthermore, it is found in the upper layers of the sky, the uppermost place, where the divine dwells." In his work Micrographia, Hooke writes, "Upon this occasion I hope it will not be altogether unreasonable if I propound my conjectures and hypothesis about the medium and conveyance of light. I suppose, then, that the greatest part of the interstitia of the world that lies between the bodies of the sun and stars and the planets and the earth to be an exceeding fluid body, very apt and ready to be moved and to communicate the motion of any one part to any other part, though never so far distant. Nor do I much concern myself to determine what the figure of the particles of this exceedingly subtle fluid medium must be, nor whether it have any interstitiated pores or vacuities, it being sufficient to solve all the phenomena to suppose it an exceedingly fluid, or the most fluid body in the world, and as yet impossible to determine the other difficulties. That being so exceeding fluid a body, it easily gives passage to all other bodies to move to and fro in it, that it neither receives from any of its parts or from other bodies, nor communicates to any of its parts or to any other body any impulse or motion in a direct line that is not of a determinate quickness, and that when the motion is of such determinate swiftness, it both receives and communicates or propagates an impulse or motion to any imaginable distance in straight lines, with an unimaginable celerity and vigor." Comparing this medium for light to the way very small quantities of a colored dye can spread quickly through a fluid medium, Hooke writes, "But the former does more nearly approach to the nature and manner of the airs being dissolved by this fluid or ether. Further, as these solutions and tinctures do alter the nature of these fluid bodies as to their aptness to propagate a motion or impulse through them, even so does the particles of the air, water, and other fluid bodies, and of glass, crystal, etc., which are commixed with this bulk of the ether, alter the motion of the propagated pulse of light. That is, where these more bulky particles are more plentiful, and consequently a lesser quantity of the ether between them to be moved, there the motion must necessarily be the swifter, though not so robust." However, in 1672, the young Isaac Newton entertained the view of light as being made of material bodies. Newton finds that color is a property of light, not a property of objects, and so concludes that light must be made of bodies that are substances. Newton writes, "These things being so, it can be no longer disputed whether there be colors in the dark, nor whether they be the qualities of the object we see, no, nor perhaps whether light be a body. For since colors are qualities of light, having its rays for their entire and immediate subject, how can we think those rays qualities also, unless one quality may be the subject of and sustain another, which in effect is to call it substance? We should not know bodies for substances were it not for their sensible qualities, and the principle of those being now found due to something else, we have as good reason to believe that to be a substance also. Besides, whoever thought any quality to be a heterogeneous aggregate such as light is discovered to be? But to determine more absolutely what light is, after what manner refracted, and by what modes or actions it produceth on our minds the phantasms of colors, is not so easy, and I shall not mingle conjectures with certainties." In that same year, Newton explains that various colors are the result of light frequency, writing, "That fundamental supposition is, that the parts of bodies, when briskly agitated, do excite vibrations in the ether, which are propagated every way from those bodies in straight lines, and cause a sensation of light by beating and dashing against the bottom of the eye, something after the manner that vibrations in the air cause a sensation of sound by beating against the organs of hearing. Now, the most free and natural application of this hypothesis to the solution of phenomena I take to be this: that the agitated parts of bodies, according to their several sizes, figures, and motions, do excite vibrations in the ether of various depths or bignesses, which being promiscuously propagated through that medium to our eyes, effect in us a sensation of light of a white color. But if by any means those of unequal bignesses be separated from one another, the largest beget a sensation of a red color, the least or shortest of a deep violet, and the intermediate ones of intermediate colors, much after the manner that bodies, according to their several sizes, shapes, and motions, excite vibrations in the air of various bignesses, which, according to those bignesses, make several tones in sound. In this time, people were not sure if light is propagated instantaneously or not, but that was resolved when in 1676 Danish astronomer Ole Rømer proved that the speed of light is finite, measuring the speed of light by subtracting the time it takes for the moon of Jupiter, Io, to enter and exit the shadow of Jupiter when the Earth is closer to Jupiter from the time it takes when the Earth is farther away from Jupiter. 2 years later, in 1678, Dutch astronomer Christian Huygens supported and developed a competing wave theory for light. In the 1600s, it was not widely thought that most of space is empty. That is, that most of space in the universe is a vacuum devoid of gas. Torricelli had created the earliest human-made vacuum on Earth in 1643, and Blaise Pascal had shown in 1648 that atmospheric pressure is less at higher elevation, which implied that empty space, in other words, a space with no air, also known as a vacuum, exists above the atmosphere of Earth. However, the traditional Aristotelian view was that nature abhors a vacuum. So it is understandable why many people in the 1600s might have thought that light must be like sound, a motion through a medium, as opposed to light being made of particles that move through space without needing any medium. It was not until the second edition of his book Optics in 1718 that Newton openly and clearly rejected a wave theory and an ether medium for light. Newton writes, "Are not all hypotheses erroneous in which light is supposed to consist in pression or motion propagated through a fluid medium?" In Optics, Newton also theorizes that rays of light are very small bodies emitted from shining substances, writing, "Are not the rays of light very small bodies emitted from shining substances? For such bodies will pass through uniform mediums in right lines without bending into the shadow, which is the nature of the rays of light." Among other criticisms, Newton contrasts the apparent rectilinear propagation of light and shadows with the propagation of sound in air, pointing out how sound, unlike light and shadows, appears to propagate in all directions and bend around objects in its path, writing, "And if it consisted in pression or motion, propagated either in an instant or in time, it would bend into the shadow, for pression or motion cannot be propagated in a fluid in right lines beyond an obstacle which stops part of the motion, but will bend and spread every way into the quiescent medium which lies beyond the obstacle." Newton instead views the space between planets and stars as mostly empty, and that any medium would slow the motion of the planets around the sun, which is not observed, writing, "And therefore, to make way for the regular and lasting motions of the planets and comets, it's necessary to empty the heavens of all matter, except perhaps some very thin vapors, steams, or effluvia, arising from the atmospheres of the earth, planets, and comets, and from such an exceedingly rare ethereal medium as we described above. A dense fluid can be of no use for explaining the phenomena of nature, the motions of the planets and comets being better explained without it." Newton goes very nearly full rebel, and crossing the proverbial Rubicon boldly concludes about an ether medium for light. So there is no evidence for its existence, and therefore it ought to be rejected. And if it be rejected, the hypotheses that light consists in pression or motion propagated through such a medium are rejected with it. As a result of Newton's work, the corpuscular theory for light will hold dominance throughout the 1700s. However, during this time, there were many people that still supported a wave theory for light, including the famous mathematician Leonhard Euler. For example, in 1746, Euler made the interesting point that in either corpuscular or wave model, the space of the universe must be full of tiny particles. In 1752, Benjamin Franklin supported a wave theory for light, writing in a letter, "I must own that I am much in the dark about light. I am not satisfied with the doctrine that supposes particles of matter called light continually driven off from the sun's surface with a swiftness so prodigious. Must not the smallest particle conceivable have, with such a motion, a force exceeding that of a 24-pounder discharged from a cannon? Must not the sun diminish exceedingly by such a waste of matter, and the planets, instead of drawing nearer to him, as some have feared, recede to greater distances through the lessened attraction? Yet these particles, with this amazing motion, will not drive before them or remove the least and lightest dust they meet with. And the sun, for aught we know, continues of his ancient dimensions, and his attendants move in their ancient orbits. May not all the phenomena of light be more conveniently solved by supposing universal space filled with a subtle elastic fluid which, when at rest, is not visible, but whose vibrations affect that fine sense the eye, as those of air do the grosser organs of the ear? We do not, in the case of sound, imagine any sonorous particles are thrown off from a bell, for instance, and fly in straight lines to the ear. Why must we believe that luminous particles leave the sun and proceed to the eye? 'Tis well we are not, as poor Galileo was, subject to the Inquisition for philosophical heresy. My whispers against the orthodox doctrine in private letters would be dangerous. Your writing and printing would be highly criminal. As it is, you must expect some censure, but one heretic will surely excuse another. In 1789, French chemist Antoine Lavoisier had published a table of elements that lists the light corpuscle as the smallest known element. However, in the early 1800s, decades after Newton's death, the view of light being made of particles that are emitted by objects and travel through empty space started to crumble. The 19th century started with some remarkable findings. Invisible frequencies of light were not known or thought about publicly until infrared light was first uncovered and measured using a prism and thermometers by German-British astronomer William Herschel in 1800. Herschel found that the invisible region beyond the red end of the visible spectrum heated up the thermometer the most. Ultraviolet light, the invisible frequencies of light with higher frequencies than visible light, was then detected by German physicist Johann Ritter 1 year later in 1801 using a prism and silver chloride. Ritter found that the silver chloride blackened most quickly in the invisible region beyond the visible violet part of the spectrum. Also in 1801, English doctor and scientist Thomas Young was the first to correctly determine the wavelength, or in the corpuscular view, the particle spatial interval, of different colors of visible light by using Newton's measurements for the thicknesses of two parallel thin glass plates and a trigonometric relation similar to what is called the Bragg equation. That Young is able to accurately measure the wavelength of different colors of visible light is a powerful support for a wave theory for light, which Young was a believer and vigorous supporter of. Also in this work, Young mentions making use of the new invention of glass gratings, a plate of glass with finely cut, evenly spaced parallel lines to separate white light into its spectrum of component colors, just as a prism does. In this same paper, Young puts forward his theory of light interference, which he explains is the result of light being a wave in a luminiferous ether, thought to be a very rare, very elastic medium filling the universe and supporting the propagation of light. This theory suggests that two light waves can add to each other or cancel each other out, similar to the way two sound waves can. Young boldly concludes his work writing, "Radiant light consists in undulations of the luminiferous ether." In 1802, spectral lines are identified as dark lines in the spectrum of a ray of light from the sun by William Wollaston. Understanding spectral absorption and emission lines will come to dominate theories of atomic composition, in particular in the 1900s. On October 21, 1803, English chemist John Dalton published a table of elements. However, unlike Lavoisier's list of elements only 14 years earlier, Dalton completely excludes the light corpuscle on his list of elements, putting instead the element hydrogen as the smallest known element. This exclusion of the light particle from the table of elements or atoms will continue to our time over 200 years later, and no doubt for a long time to come. A month later, on November 24, 1803, Thomas Young published his claim of experimental proofs of light interference, building on Grimaldi's diffraction experiments of 1665. Grimaldi had found that light passed through two holes, one in front of the other, produced light outside of the cone of light expected. Instead of Grimaldi's apparatus, Young uses a short side of a thin card to split a beam of light from the sun, which reveals bands of light and dark lines in the shadow, thought to be the result of light waves interfering with each other. In the case of light bands, light waves are thought to be adding to each other, and the dark bands are explained as light waves canceling each other out. Young writes, "I have found so simple and so demonstrative a proof of the general law of the interference of two portions of light, which I have already endeavored to establish, that I think it right to lay before the Royal Society a short statement of the facts which appear to me so decisive. The proposition on which I mean to insist at present is simply this, that fringes of color are produced by the interference of two portions of light. I brought into the sunbeam a slip of card about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of color on each side of the shadow itself was divided by similar parallel fringes of smaller dimensions." Young concludes this paper by comparing interference of light waves to interference of sound waves and support for an all-pervasive luminiferous ether, writing, "Since we know that sound diverges in concentric superficies, and that musical sounds consist of opposite qualities, capable of neutralizing each other, and succeeding at certain equal intervals, which are different according to the difference of the note, we are fully authorized to conclude that there must be some strong resemblance between the nature of sound and that of light. I am disposed to believe that the luminiferous ether pervades the substance of all material bodies with little or no resistance, as freely perhaps as the wind passes through a grove of trees." In 1807, Young publishes his book, A Course of Lectures on Natural Philosophy and the Mechanical Arts, which includes a description and diagrams describing a double hole or double slit experiment to produce wave interference, in this case using water and then light. Young describes and provides diagrams showing the patterns produced by moving water passing through two openings, and then goes on to show similar patterns that he has observed for light passing through a screen with two openings. Young writes, "Supposing the light of any given color to consist of undulations of a given breadth or of a given frequency, it follows that these undulations must be liable to those effects which we have already examined in the case of the waves of water and the pulses of sound. It has been shown that two equal series of waves proceeding from centers near each other may be seen to destroy each other's effects at certain points, and at other points to redouble them, and the beating of two sounds has been explained from a similar interference. We are now to apply the same principles to the alternate union and extinction of colors. In order that the effects of two portions of light may be thus combined, it is necessary that they be derived from the same origin, and that they arrive at the same point by different paths, in directions not much deviating from each other. This deviation may be produced in one or both of the portions by diffraction, by reflection, by refraction, or by any of these effects combined. But the simplest case appears to be when a beam of homogeneous light falls on a screen in which there are two very small holes or slits, which may be considered as centers of divergence, from whence the light is diffracted in every direction. In this case, when the two newly formed beams are received on a surface placed so as to intercept them, their light is divided by dark stripes into portions nearly equal, but becoming wider as the surface is more remote from the apertures, so as to subtend very nearly equal angles from the apertures at all distances. and wider also in the same proportion as the apertures are closer to each other. The middle of the two portions is always light, and the bright stripes at each side are at such distances that the light coming to them from one of the apertures must have passed through a longer space than that which comes from the other, by an interval which is equal to the breadth of 1, 2, 3, or more of the supposed undulations, while the intervening dark spaces correspond to a difference of half a supposed undulation of 1½ or 2½ or more. Note that bands of light and dark can be produced even with a single slit, and is the same phenomenon first described by Grimaldi in 1665, which he named diffraction. One criticism of the theory that these light bands produced by narrow slits or holes, or in the shadow of small obstructing objects, such as a thin card, strand of hair, or wire, are due to the interference of waves of light, is that introducing an apparatus creates the problem of reflection of light off of the material the object is made of. It seems logical that true light interference, that is, light waves interfering with each other alone, should not depend on any apparatus, as is the case for sound interference. If light waves truly interfere with themselves, no apparatus should be necessary to see interference patterns. A simple experiment could be having two monochromatic light sources pointed in two different but intersecting directions, in order to interfere with each other and to show that similar light and dark bands are produced where the two waves add and cancel each other out. I was unable to observe any interference pattern from two LEDs with narrow frequencies of light. However, this simple experiment should be reproduced with a wide variety of monochromatic light frequencies of both visible and invisible frequency, in conjunction with mathematical calculation of where the various interference bands should appear. So the corpuscular view of light had seemingly largely fallen out of favor in scientific circles in England by 1803. The wave theory, also called the undulatory theory for light at this time, was strictly believed to be as Descartes and Hooke had imagined, a motion that is transmitted through the collision of material particles that fill the universe, the wave being a longitudinal wave. In 1808, Etienne Louis Malus discovered the phenomenon of what is commonly now called light polarization. According to French physicist François Arago, one day in his house in the Rue des Enfers, Malus happened to examine through a doubly refracting crystal. Iceland spar, also called optical calcite, is a transparent variety of calcite, the rays of the sun reflected from the windows of the Luxembourg Palace. Instead of two bright images which he expected to see, he perceived only one, the ordinary or the extraordinary, according to the position which the crystal occupied before his eye. This singular phenomenon struck him much. Malus names this phenomenon polarization, theorizing that light corpuscles have polarity like magnetic poles. But in my mind, other theories are possible. For example, part of a light beam can be transmitted through a surface and part reflected to produce two images, as shown by rotating a glass slide with a laser beam. In addition, this simulation shows how a particle theory for light can possibly explain the phenomenon of polarization. See how the direction of the light is filtered to only include light particles going in the same direction as the planes in a polarizing material. In this sense, polarization might be more accurately named planarization, because the light is filtered by light ray direction into a single plane. Unfortunately, corpuscular explanations for the phenomenon of polarization of light appear to be largely absent in our time. This new finding of polarization prompted new efforts to explain the polarization phenomenon within either the corpuscular or the undulatory theory framework. The transverse wave theory for light arose from an effort to try to explain the phenomenon of polarization while maintaining the undulatory theory of light. In 1816, French physicists Arago and Fresnel find that two rays polarized at right angles to each other never interfere. That is, they do not show interference patterns in the shadow of an obstructing small metal cylinder. describing their experiment where a light beam split into two beams by double refracting calcite that results in the two beams being polarized at right angles to each other, which do not produce interference patterns in the shadow of an obstructing object. Arago and Fresnel write, translated from French. It was still to be determined whether two rays originally polarized at right angles would not produce phenomena of the same kind when they met inside the geometrical shadow of an opaque body. For this purpose, we placed in front of the point source. For all of the experiments described in this paper, our source of light was the focus of a small magnifying glass, sometimes a rhomb of calcspar, sometimes an achromatic prism of rock crystal, and thus obtained two luminous points. In each case, we had a divergent pencil, and these two pencils were polarized at right angles. Behind the two radiant points and midway of the space between them was placed a cylinder of metal. In this manner, a part of the polarized light from the first pencil reached the interior of the shadow via the right-hand side of the cylinder, while a part of the light from the second pencil, polarized in a plane at right angles to the first, entered the shadow from the left-hand side of the cylinder. Some of these rays met along the line joining the center of the cylinder and the middle point of the straight line drawn from one luminous point to the other. Here these rays had traversed equal paths, and one might expect them to produce fringes. On the contrary, not the slightest trace of fringes could be seen, even with a magnifying glass. In fact, the rays here cross without either affecting the other. The only fringes which make their appearance in this experiment arise from the interference of rays which come from only one of the radiant points and enter the shadow from either side of the cylinder. Those which we tried to produce by the interference of rays polarized at right angles to each other would have occupied a position intermediate between those just mentioned. One natural question about this experiment that arises in my mind is, why is a metal cylinder needed to cause the interference to be observed? Would not the interference of these two beams appear without an obstructing object if the two beams were truly waves in a material particle medium? Another question I have about this experiment is, although there appears to be no interference pattern in the shadow of the metal cylinder, why are there interference patterns on the sides? Are the individual beams of light interfering with themselves? Perhaps those interference patterns are actually the result of a grating phenomenon from equally spaced rows of atoms on the surface of the metal cylinder. In an effort to explain the new finding of light polarization within an undulatory theory framework, Young suggests in a letter to Arago on January 12, 1817, that light waves may result in additional transverse waves. That is, in addition to the regular vibration of light, light waves may cause a vibration in a direction sideways to their direction of motion. Young writes, I have also been reflecting on the possibility of giving an imperfect explanation of the affection of light which constitutes polarization, without departing from the genuine doctrine of undulations. It is a principle in this theory that all undulations are simply propagated through homogeneous mediums in concentric spherical surfaces, like the undulations of sound, consisting simply in the direct and retrograde motions of the particles in the direction of the radius, with their concomitant condensation and rarefactions. And yet it is possible to explain in this theory a transverse vibration, propagated also in the direction of the radius, and with equal velocity, the motion of the particles being in a certain constant direction with respect to that radius. And this is a polarization, but its inconceivable minuteness suggests a doubt as to the possibility of its producing any sensible effects. In a physical sense, it is almost an evanescent quantity, although not in a mathematical one. Its foundation is this. Suppose two particles to reflect two portions of light which interfere with each other and form a dark fringe, the one being situated at the distance of several intervals from the other, in a direction transverse to that of the fringe. It is obvious that their interference can never be so completely effectual as not to leave some remains of the motions combined with each other. The direct motion of the one will destroy the retrograde motion of the other, but the transverse motions of each, with respect to the line bisecting their directions, will conspire with each other and will produce a single transverse vibratory motion. And who shall say that this motion will be too minute to produce any effect in any circumstances? In Young's 1817 work titled Chromatics, Young gives more details about how he envisions an undulatory theory that includes a transverse motion that can explain how a beam of light split into two beams polarized at 90 degrees to each other do not interfere with each other. Young writes, "The experiments of Mr. Arago, not yet published in detail, which show that light does not interfere with light polarized in a transverse direction, lead us immediately to the consideration of the general phenomena of polarization, which cannot be said to have been by any means explained on any hypothesis respecting the nature of light. It is certainly easier to conceive a detached particle, however minute, distinguished by its different sides, as having a particular axis turned in a particular direction, than to imagine how an undulation, resembling the motion of the air which constitutes sound, can have any different properties with respect to the different planes which diverge from its path." But here the advantage of the projectile theory ends, for every attempt to reduce the phenomena of polarization to mechanical laws, by the analogy of magnetism, has completely failed of enabling us to calculate the results of the actions of the forces supposed to be concerned in any correct manner, to say nothing of the extreme complication of the properties, which it would be necessary to attribute to the simplest and minutest substances. In order to justify the original hypothesis of a polarity existing in all the particles of light, and a directive attraction, that is, a combination of attraction and repulsion, in every reflecting or refracting substance. In the undulatory theory, we may discover some distant analogies, sufficient to give us a conception of the possibility of reconciling the facts with the theory, and perhaps even of reducing those facts to some general laws derived from it, although it will be necessary, in this intricate part of the inquiry, to proceed analytically rather than synthetically, and to rest satisfied for the present, without bringing the analysis to a termination by any means explanatory of all the phenomena. Some of the supporters of this theory may perhaps be of opinion that its deficiencies are too strongly displayed by this attempt, but it is for them to find a more complete solution of the difficulties, if any such can be discovered. In the case of a wave moving on the surface of a liquid, considering the motion of the particles at some little distance below the surface, as concerned in the propagation of an undulation in a horizontal direction, we may observe that there is actually a lateral motion throughout the liquid in a plane of which the direction is determined by that of gravitation. But this happens because the liquor is more at liberty to extend itself on this side than on any other, the force of gravitation tending to bring it back, with a pressure of which the operation is analogous to that of elasticity. And we cannot find a parallel for this force in the motions of an elastic medium. It is indeed very easy to deduce a motion transverse to the general direction from the combination of two undulations proceeding from two neighboring points, and interfering with each other when the difference of their paths amounts to half an interval. For the result of this combination will be a regular, though a very minute, vibration in a transverse direction, which will continue to take place throughout the line of the propagation of the joint motions, although certainly not with any force that would naturally be supposed capable of producing any perceptible effects. There must even be a difference in the motions of the particles in every simply diverging undulation, in different parts of the spherical surface to which they extend. For supposing it to originate from a vibration in a given plane, the velocity of the motion constituting the undulation will be greatest in the direction of that plane, and will disappear in a direction perpendicular to it, or rather will there become transverse to the direction of the diverging radii. And in all other parts there must be a very minute tendency to a transverse motion, on account of the difference of the velocities of the collateral direct motions, and of the compressions and dilations which they occasion. When also a limited undulation is admitted into a quiescent medium, it loses some of its force by diffraction on each side, where it is unsupported by the progress of the collateral parts. And if an undulation were admitted by a number of minute parallel linear apertures, or slits, or reflected from an infinite number of small wires, parallel to each other, it would still retain the impression of the incipient tendency to diffraction in all its parts, producing a modification of the motion in a direction transverse to that of the slits or wires. It is true that all these motions and modifications of motion would be minute beyond the power of imagination, even when compared with other motions themselves extending to a space far too minute to be immediately perceived by the senses. And this consideration may perhaps lessen the probability of the theory as a physical explanation of the facts, but it would not destroy its utility as a mathematical representation of them, provided that such a representation could be rendered general and reducible to calculation. And even in a physical sense, if the alternative were unavoidable, it is easier to imagine the powers of perceiving minute changes to be all but infinite than to admit the portentous complication of machinery which must be heaped up in order to afford a solution of the difficulties which beset the application of the doctrine of simple projection to all the phenomena of polarization and of colors. It is not, however, possible at present to complete such a mathematical theory, even on imaginary grounds, although a few further analogies between polarization and transverse motion force themselves on our observation. In the theory of emission, the resemblance of the phenomena of polarization to the selection of a certain number of particles having their axes turned in a particular direction, supposing these axes, like those of the celestial bodies, to remain always parallel, will carry us to a certain extent in estimating the quantity of light contained in each of the two pencils into which a beam is divided and subdivided. But it would soon appear that after a few modifications, this parallelism could no longer be supposed to be preserved. We should also find it impossible to assign the nature and extent of any forces which might be capable of changing the former directions of the axes and fixing them permanently in new ones. The distinction of a fixed, a movable, and a partial polarization, which has been imagined by Mr. Biot, must vanish altogether upon considering that all the effects which he attributes to the partial polarization are observable in experiments like those of Mr. Knox, in which there is confessedly no polarization at all. If we assume as a mathematical postulate in the undulatory theory, without attempting to demonstrate its physical foundation, that a transverse motion may be propagated in a direct line, we may derive from this assumption a tolerable illustration of the subdivision of polarized light by reflection in an oblique plane. Supposing polarization to depend on a transverse motion in the given plane, when a ray completely polarized is subjected to simple reflection in a different plane, which is destitute of any polarizing action, and may therefore be called a neutral reflection, the polar motion may be conceived to be reflected, as any other motion would be reflected at a perfectly smooth surface, the new plane of the motion being always the image of the former plane, and the effect of refraction will be nearly of a similar nature. But when the surface exhibits a new polarizing influence, and the beams of light are divided by it into two portions, the intensity of each may be calculated by supposing the polar motion to be resolved instead of being reflected, the simple velocities of the two portions being as the cosines of the angles formed by the new planes of motion with the old, and the energies, which are the true measure of the intensity, as the squares of the sines. We are thus insensibly led to confound the intensity of the supposed polar motion with that of the reflected light itself, since it was observed by Malus that the relative intensity of the two portions into which light is divided under such circumstances is indicated by the proportion of the squares of the cosine and sine of the inclination of the planes of polarization. The imaginary transverse motion might also necessarily be alternate, partly from the nature of a continuous medium, and partly from the observed fact that there is no distinction between the polarizations produced by causes precisely opposed to each other in the same plane. Notice the early use of the word energy by Young, energy being the product of mass and velocity squared, originally described by German mathematician Gottfried Leibniz, and named by Leibniz vis viva, the living force. Young was the first to introduce this concept into England, referring to this quantity Leibniz named vis viva, using the word energy. The quantity energy will dominate much of the 1800s and 1900s scientific thought and publication. Reading Thomas Young's description of how he envisions this transverse motion of a light wave, it seems that Young is still maintaining a longitudinal wave structure for light and simply saying that some aspect of the motion of the wave, while primarily and most dominantly in the forward or 0 degrees direction of the motion, must cause some motions in other directions due to collisions with particles in the medium that are on the sides of the primary motion. The motion of the light wave being most in the direction of motion and causing less and less motion to the side of the wave progressively from 0 to 90 degrees. So as the wave motion pushes forward through the light particle medium, due to the collision of light medium particles on the sides, there is a small sideways motion. And just like the forward motion, these sideways motions cause oscillations as the light medium particles collide with other light medium particles that reflect back in the opposite direction. If true, then it seems logical that there would be not only small oscillations at 90 degrees to the direction of motion, but also at many of the other angles in between 0 and 90 degrees. In fact, it seems reasonable to estimate that the amount of motion in those other directions would be even more than the oscillating motion that results at 90 degrees to the primary motion of the wave, in proportion to the cosine of the angle made with the primary direction of motion. So I think that there is an argument to be made that Young always envisioned light as being a longitudinal wave, a transverse wave being simply a subset and consequence of a longitudinal wave. In fact, later on in 1881, one scientist, S.W. Robinson, will try to reconcile the theory of polarization due to transverse motion with waves of sound, claiming that a transverse motion must be characteristic of all undulations, including those for sound. The author writes, "If ether undulations can be polarized, why not undulations generally?" When comparing to sound, that polarization of light is maintained after the light gets past the polarizing material, I think is evidence for a corpuscular theory. Otherwise, would not the particle collisions resume colliding with other light medium particles in an unrestricted way, sending light in a semi-spherical direction upon exiting the polarizing material, therefore losing the polarization? Thinking about the motion of light particles versus light medium particles, the problem of dissipation of motion, or the dissipation of so-called energy, seems to be more of a problem for the wave theory. This is because with each light-medium particle collision, some of that motion must be lost to collisions with light-medium particles to the sides, as opposed to the corpuscular theory, where there is, presumably, no collision that would result in distributing motion to other particles. Since light particles are presumably maintaining their initial motion without any friction. This may be why the motion from a motion source in water or in air, even a constantly oscillating motion source, dissipates much more quickly and in a shorter distance in the direction of motion than we see light dissipate in the direction of motion. Note that the theory I am putting forward here and displayed in this three-dimensional model simulation showing how a corpuscular explanation for light polarization might be visualized is different from the corpuscular theory to explain polarization in 1817. The theory I am explaining is that a polarizing material restricts the direction of light particle beams and has nothing to do with the shape of light particles themselves. One possible corpuscular theory explanation for the reason that a light beam split into two beams polarized at 90 degrees to each other do not produce interference patterns is that the spectrum produced by the regularly spaced rows of atoms in the obstructing object, similar to a diffraction grating, depend on the angle of incident light, and if the incident light occupies only a single plane, the number of light particles reflected to produce a spectrum is smaller. Note that I am thinking of a beam of light from a spherical light source that is vertically polarized, being sent to a horizontal grating at various angles. Another possible explanation is that light particles collide with each other to produce interference patterns, and far fewer collisions happen when the two light beams occupy two planes that are at 90 degrees to each other. In 1818, a prize for an explanation of the phenomenon of diffraction by the Paris Academy was won by Augustin Fresnel, who based his explanation on a wave theory for light. Famous physicist Max Born explains in his History of Optics that this work, quote, was the first of a succession of investigations which, in the course of a few years, were to discredit the corpuscular theory completely. The substance of his memoir consisted of a synthesis of Huygens envelope construction with Young's principle of interference. This, as Fresnel showed, was sufficient to explain not only the rectilinear propagation of light, but also the minute deviations from it, diffraction phenomena. Fresnel calculated the diffraction caused by straight edges, small apertures, and screens. End quote. As a result of Fresnel's theory, French mathematician Simeon Poisson showed that if Fresnel's theory is correct, then a bright spot should appear in the center of the shadow from a small circular disk. French physicist François Arago observed the spot experimentally in 1819, and this was a large apparent victory for the wave theory for light. This spot is often called the Arago or Poisson spot, and is a spot of light in the center of a round shadow made by monochromatic light that is thought to arise from the interference of light waves that exist in the shadow. This spot can be observed using a laser and spherical object to obstruct the laser light, like a ball bearing or marble. A corpuscular explanation of this spot could be that light particle dispersion due to reflection causes the spot, since at the edge of a circular object light particles can be reflected inward due to the regular atomic structure of the object, similar to how a grating works. That this experiment requires very specific conditions to produce interference patterns, and generally speaking, we never see any light in the shadow of the vast majority of objects with monochromatic light or otherwise, implies to me at least that these light patterns in the shadow are the result of the very few light particles that reflect off atomic structure to produce the classic faintly lit spectrum pattern. Particle reflection is very difficult to avoid, since all matter reflects light in some way, although there are some materials that reflect very little light, like charcoal and Vanta black. Vanta black is composed of a forest of vertical carbon nanotubes grown on a substrate using a modified chemical vapor deposition process. When light strikes Vanta black, instead of bouncing off, it becomes trapped and continually deflected amongst the tubes, absorbed and eventually dissipated as heat. In addition, the theory that within a monochromatic beam split into two parts are light particles that collide with each other, causing the interference patterns, could provide a possible explanation of the Arago-Poisson spot. So in France at this time, a wave theory for light had the support of famous French physicists Arago and Fresnel, but not Biot and Laplace, who still publicly held to the corpuscular theory. However, over the course of time, Young's transverse theory would take hold and completely topple the corpuscular theory of light as the last of the major remaining supporters of the corpuscular view died off. Fast forward to 1845, when English chemist Michael Faraday finds that plane polarized light is found to rotate when passed through glass subjected to an electromagnetic field. Faraday focused many experiments in an effort to find a relation between electromagnetism and light. 19 years later, in 1864, Scottish physicist James Clerk Maxwell will refer to this finding when creating his electromagnetic wave theory for light, the currently most widely accepted theory for light. More support for a wave theory for light came in 1850 when French physicist Léon Foucault had shown that light takes more time to pass through water than the less dense medium of air. This is thought to be proof against a corpuscular, also sometimes called an emission, theory for light, because the prevailing view was that light corpuscles would move through a denser medium faster than a less dense medium, because it was thought that refraction is the effect of an attractive force directed to a denser medium. However, in my mind, it makes sense that light particles would have a longer travel path in a denser medium because of an increase in the number of particle collisions. In 1851, French physicist Hippolyte Fizeau performed a famous experiment to measure the relative speeds of light in moving water. It was thought at the time that light traveling through a moving medium will be dragged along by the medium, so that the measured speed of light will be the sum of the speed of light through the medium plus the speed of the medium itself. However, Fizeau finds very little change in the speeds of light through moving water and no change in the speeds of light through moving air. This experiment will go on to inspire explanations from Fresnel and later the theoretical physicists Hendrik Lorentz and Albert Einstein. Thinking of a corpuscular explanation for why the speed of light might be slightly faster in moving water than through stationary water, perhaps light particles trapped in the many corridors within a tank of water reach the target slightly sooner than when the water molecules are not collectively moving, while light particles are probably delayed far less in moving air, making any decrease in arrival time too small to measure. In 1855, German physicists Kohlrausch and Weber conclude that an electrical mass will not be influenced by the electrical force if moving with a velocity at least the speed of light. This will play an influential role in James Clerk Maxwell's creation of a theory that light is an electromagnetic wave in an ethereal medium. In 1864, James Clerk Maxwell publishes his theory of the electromagnetic field and the theory that light is actually an electromagnetic wave in a material ethereal medium. Relating his dissatisfaction with the contemporary action at a distance theories of electric and magnetic phenomena, Maxwell writes, "The mechanical difficulties, however, which are involved in the assumption of particles acting at a distance with forces which depend on their velocities, are such as to prevent me from considering this theory as an ultimate one, though it may have been, and may yet be useful in leading to the coordination of phenomena. I have therefore preferred to seek an explanation of the fact in another direction, by supposing them to be produced by actions which go on in the surrounding medium as well as in the excited bodies, and endeavoring to explain the action between distant bodies without assuming the existence of forces capable of acting directly at sensible distances. The theory I propose may therefore be called a theory of the electromagnetic field, because it has to do with the space in the neighborhood of the electric or magnetic bodies, and it may be called a dynamical theory because it assumes that in that space there is matter in motion, by which the observed electromagnetic phenomena are produced. The electromagnetic field is that part of space which contains and surrounds bodies in electric or magnetic conditions. It may be filled with any kind of matter, or we may endeavor to render it empty of all gross matter, as in the case of Geissler's tubes and other so-called vacua. There is always, however, enough of matter left to receive and transmit the undulations of light and heat, and it is because the transmission of these radiations is not greatly altered when transparent bodies of measurable density are substituted for the so-called vacuum that we are obliged to admit that the undulations are those of an ethereal substance, and not of the gross matter, the presence of which merely modifies in some way the motion of the ether. We have therefore some reason to believe, from the phenomena of light and heat, that there is an ethereal medium filling space and permeating bodies capable of being set in motion, and of transmitting that motion from one part to another, and of communicating that motion to gross matter so as to heat it and affect it in various ways. Now, the energy communicated to the body in heating it must have formerly existed in the moving medium, for the undulations have left the source of heat some time before they reached the body, and during that time the energy must have been half in the form of motion of the medium and half in the form of elastic resilience. We may therefore receive, as a datum derived from a branch of science independent of that which we have to deal, the existence of a pervading medium of small but real density, capable of being set in motion, and of transmitting motion from one part to another with great but not infinite velocity. Talking about an apparent connection between the effect of a magnetic field on light, Maxwell writes, "Now we know that the luminiferous medium is in certain cases acted on by magnetism, for Faraday discovered that when a plane polarized ray traverses a transparent diamagnetic medium in the direction of the lines of magnetic force produced by magnets, or currents in the neighborhood, the plane of polarization is caused to rotate. This rotation is always in the direction in which positive electricity must be carried round the diamagnetic body in order to produce the actual magnetization of the field. M. Verde has since discovered that if a paramagnetic body, such as solution of perchloride of iron in ether, be substituted for the diamagnetic body, the rotation is in the opposite direction. Note that a dielectric is a form of insulator located between the plus and minus electrodes of a capacitor and has the property of storing electricity. Diamagnetic materials are slightly repelled by a magnetic field, but paramagnetic materials are slightly attracted by a magnetic field. Both diamagnetic and paramagnetic materials do not retain the magnetic properties when the external field is removed. As an aside, I think we cannot rule out that the effect of a magnetic field changes the physical structure of the material Faraday used to rotate the plane of plane polarized light. For example, perhaps the particles in the magnetic field cause atomic structures in the material, like little mirrors, to slightly rotate, which changes the direction the plane polarized light particles are reflected. In that case, the light is not being directly moved by the magnetic field, but only indirectly moved as a result of changes to physical structure in the material the light passes through. Maxwell continues discussing the implication of Faraday's experiment, which found an apparent effect of magnetism on light. Now, Professor W. Thompson has pointed out that no distribution of forces acting between the parts of a medium whose only motion is that of the luminiferous vibrations is sufficient to account for the phenomena, but that we must admit the existence of a motion in the medium depending on the magnetization, in addition to the vibratory motion which constitutes light. It is true that the rotation by magnetism of the plane of polarization has been observed only in media of considerable density, but the properties of the magnetic field are not so much altered by the substitution of one medium for another, or for a vacuum, as to allow us to suppose that the dense medium does anything more than merely modify the motion of the ether. We have therefore warrantable grounds for inquiring whether there may not be a motion of the ethereal medium going on wherever magnetic effects are observed, and we have some reason to suppose that this motion is one of rotation, having the direction of the magnetic force as its axis. We may now consider another phenomenon observed in the electromagnetic field. When a body is moved across the lines of magnetic force, it experiences what is called an electromotive force. The two extremities of the body tend to become oppositely electrified, and an electric current tends to flow through the body. When the electromotive force is sufficiently powerful and is made to act on certain compound bodies, it decomposes them and causes one of their components to pass toward one extremity of the body and the other in the opposite direction. Here we have evidence of a force causing an electric current in spite of resistance, electrifying the extremities of a body in opposite ways, a condition which is sustained only by the action of the electromotive force, and which, as soon as that force is removed, tends, with an equal and opposite force, to produce a countercurrent through the body and to restore the original electrical state of the body, and finally, if strong enough, tearing to pieces chemical compounds and carrying their components in opposite directions, while their natural tendency is to combine, and to combine with a force which can generate an electromotive force in the reverse direction. This, then, is a force acting on a body caused by its motion through the electromagnetic field, or by changes occurring in that field itself, and the effect of the force is either to produce a current and heat the body, or to decompose the body, or, when it can do neither, to put the body in a state of electric polarization, a state of constraint in which opposite extremities are oppositely electrified, and from which the body tends to relieve itself as soon as the disturbing force is removed. According to the theory which I propose to explain, this electromotive force is the force called into play during the communication of motion from one part of the medium to another, and it is by means of this force that the motion of one part causes motion in another part. When electromotive force acts on a conducting circuit, it produces a current, which, as it meets with resistance, occasions a continual transformation of electrical energy into heat, which is incapable of being restored again to the form of electrical energy by any reversal of the process. But when electromotive force acts on a dielectric, it produces a state of polarization of its parts, similar in distribution to the polarity of the parts of a mass of iron under the influence of a magnet, and, like the magnetic polarization, capable of being described as a state in which every particle has its opposite poles in opposite conditions. In a dielectric under the action of electromotive force, we may conceive that the electricity in each molecule is so displaced that one side is rendered positively and the other negatively electrical, but that the electricity remains entirely connected with the molecule and does not pass from one molecule to another. The effect of this action on the whole dielectric mass is to produce a general displacement of electricity in a certain direction. This displacement does not amount to a current because when it has attained to a certain value it remains constant, but it is the commencement of a current, and its variations constitute currents in the positive or the negative direction, according as the displacement is increasing or decreasing. In the interior of the dielectric there is no indication of electrification, because the electrification of the surface of any molecule is neutralized by the opposite electrification of the surface of the molecules in contact with it. But at the bounding surface of the dielectric, where the electrification is not neutralized, we find the phenomena which indicate positive or negative electrification. Talking about how he created 20 equations to be able to uniformly describe a wide variety of electric and magnetic phenomena, Maxwell writes, "In order to bring these results within the power of symbolic calculation, I then express them in the form of the general equations of the electromagnetic field. There are 20 of these equations in all, involving 20 variable quantities." Moving on to the theory of light being an electromagnetic wave, Maxwell continues, "The general equations are next applied to the case of a magnetic disturbance propagated through a non-conducting field, and it is shown that the only disturbances which can be so propagated are those which are transverse to the direction of propagation, and that the velocity of propagation is the velocity v, found from experiments such as those of Weber, which expresses the number of electrostatic units of electricity which are contained in one electromagnetic unit. The velocity is so nearly that of light that it seems we have strong reason to conclude that light itself, including radiant heat and other radiations if any, is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field according to electromagnetic laws. If so, the agreement between the elasticity of the medium as calculated from the rapid alternations of luminous vibrations and as found by the slow process of electrical experiments shows how perfect and regular the elastic properties of the medium must be when not encumbered with any matter denser than air. If the same character of the elasticity is retained in dense transparent bodies, it appears that the square of the index of refraction is equal to the product of the specific dielectric capacity and the specific magnetic capacity. Conducting media are shown to absorb such radiations rapidly and therefore to be generally opaque. The conception of the propagation of transverse magnetic disturbances to the exclusion of normal ones is distinctly set forth by Professor Faraday in his Thoughts on Ray Vibrations. The electromagnetic theory of light, as proposed by him, is the same in substance as that which I have begun to develop in this paper, except that in 1846 there were no data to calculate the velocity of propagation. Later, by 1873, Maxwell had extended Young's transverse wave theory to describe light as being made of not one, but of two transverse waves, and then one of the waves being an electric wave, the other being a magnetic wave. This is a diagram Maxwell published to make clearer his visualization of a light wave. You can see that in his view, both the electric and magnetic part of a light wave can be viewed as having a sine wave shape at 90 degrees to each other and transverse to the primary direction of the light. Maxwell prohibited women from working in the Cavendish laboratory under his leadership, and not that this necessarily invalidates his dual transverse electromagnetic theory. It does go to show that much has changed since that time, and that Maxwell had at least one outdated and unrealistic viewpoint. Heinrich Hertz will go on in 1887 to perform experiments that result, among other things, in sending the invisible waves of electromagnetic induction, that is, of invisible light emitted from electric current, which will come to be called radio waves, from one wire to another disconnected wire by oscillating the current at specific frequencies. Hertz will reference Maxwell's light is an electromagnetic wave theory as a starting point in this research. From a corpuscular standpoint, without trying to offend anyone's sensibilities or to cast myself as knowing more than these ingenious savants, I cannot help but think that radio waves might be the result of particles of electricity, electrons and ions, etc., knocking loose light particles, which are emitted from conductors as the particles of electricity travel through conductive material. One apparent problem, specifically with a transverse wave theory for light, is the possible problem of how very low frequencies of light would have to have a wave size that must cover an extremely large distance. If light is a wave that has a horizontal or vertical amplitude, that is, an amplitude in the x or y dimension in the direction of travel, and the light has a very low frequency, say 1 nanohertz, one wave every 1 billion seconds, if this wave is a typical sine wave, the maximum amplitude of that sine wave would be exactly equal to 1/4 of the wavelength, which for light is lambda equals velocity divided by frequency, and that is 3 times 10 to the power 8 meters per second divided by 1 times 10 to the power minus 9 hertz divided by 4, and that equals 7.5 times 10 to the power 16 meters, a great distance. The moon of Earth is only 4 times 10 to the power 8 meters from Earth. Jupiter is only 7 times 10 to the power 11 meters from Earth. The nearest star system to us, Alpha Centauri, is only 4 times 10 to the power 16 meters away. So this light wave that starts on Earth with a very low frequency and a giant wavelength must have to be pushing ether corpuscles out past Alpha Centauri, while for a corpuscular theory, light particles only have to travel forward in a single dimension with no regard to the frequency. Perhaps a supporter of a wave theory for light that has a transverse component might argue that, as Young had acknowledged, the transverse portion of a light wave is very small compared to the forward motion of a light wave, and so perhaps this transverse component dissipates quickly and simply does not reach Centauri, while the forward motion continues over a much larger distance. Another interesting characteristic of either a single or double transverse wave for light would be the requirement of light to actually be moving, if in a sine wave motion, faster than the observed speed of light in a straight line, having to trace out a sine wave shape for each wave node. Presumably, a light beam appears to move in a straight line. However, according to this theory, the light impulse is physically moving in a sine wave, so how can the light beam be detected in between wave nodes? So comparing the two views, corpuscular and undulatory, in the case of light falling upon and heating up some object or stimulating fluorescence in a fluorescent material, with the corpuscular view, light particles enter into solid objects and get trapped within the many corridors and tunnels made by atoms that material objects are made of, the light particles adding their motion to other particles and atoms the object is made of, while the undulatory theory views this phenomenon by viewing the tiny light medium particles as filling all of space, including within all material objects, and so the motion of the light waves colliding with the object pass that motion on to the light particles in the medium and to the larger atoms the object is made of, to cause that added motion to get trapped within an object. The necessity of a medium for light for a wave theory for light has been a point of contention for many years, and this debate, centered on the question of, does an ether medium for light exist, became a primary focus of attention when in 1881 Prussian-born U.S. physicist Albert Michelson, with financial assistance from Alexander Graham Bell, used his light interferometer to prove that a beam of light horizontal to the surface of Earth, split into two beams moving at directions 90 degrees to each other, travels at the same speed, which would not be the case if the Earth was moving through a stationary luminiferous ether. Michelson's interferometer is a device that splits a beam of light into two using a half-silvered mirror, and then reflects those two beams back together to form an interference pattern that occurs when the two beams have traveled over different distances. Michelson boldly concludes this famous work with the words, "The result of the hypothesis of a stationary ether is thus shown to be incorrect, and the necessary conclusion follows that the hypothesis is erroneous." In 1885, the Balmer series is discovered, a simple mathematical formula that gives the wavelengths of the spectral emission lines of hydrogen. This application of a mathematical formula to an observed series of regularly spaced emitted light frequencies will start a long thread of thought, theories, and publications that will ultimately lead to the Bohr model of the atom, where electrons orbiting an atom nucleus either absorb or emit light, resulting in the electron changing between precise orbits, corresponding to the frequencies of light absorbed or emitted from them, as shown by their light spectrum. And this will also lead to the current view of subatomic matter, in which subatomic matter is described by wave functions. In 1887, Albert Michelson's 1881 experiment that fails to detect an ether medium for light was more famously performed a second time, this time with the added weight of the academic scientist Edward Morley, and this is traditionally called the famous Michelson-Morley experiment. A few years later, in 1889, Irish physicist George Fitzgerald provided a possible explanation to save the theory of an ether medium for light in a small paragraph published in the journal Science. Fitzgerald suggested that matter in motion, in this case the planet Earth and everything moving with the planet Earth, like the measuring apparatus, compresses itself depending on its speed relative to the speed of the light, in a direct relation, so that the speed of light appears to be the same in every direction regardless of the motion of the measuring apparatus relative to the ethereal medium. Dutch physicist Hendrik Lorentz extended this idea in 1899 to include changes in mass and even changes in time itself depending on the motion of matter. Michelson appears to have rejected both of these claims, writing in his 1927 Studies in Optics, Lorentz and Fitzgerald have proposed a possible solution of the null effect of the Michelson-Morley experiment by assuming a contraction in the material of the support for the interferometer just sufficient to compensate for the theoretical difference in path. Such a hypothesis seems rather artificial, and it of course implies that such contractions are independent of the elastic properties of the material. However, famous theoretical physicist Subrahmanyan Chandrasekhar, roundly lowering the boom and giving Michelson the smackdown, explicitly criticizes any doubts such as Michelson's in a note in the beginning of the 1968 reprint, writing, "In describing these ideas bearing on special relativity, Professor Michelson adopts a cautious attitude, sometimes giving the impression of skepticism. Such an attitude was justifiable at the time in view of the revolutionary character of the theory. However, at the present time, the experimental basis for special relativity is so wide and the theoretical ramifications so many that there can no longer be any doubt about its validity." Although I think most of what is considered experimental evidence for the special theory of relativity was performed prior to the 1927 printing of Michelson's Studies in Optics. These space and time, and some may argue mind and perhaps spoon-bending explanations of Fitzgerald and Lorentz somehow won the consensus of scientific minds, in particular when famous German-born theoretical physicist Albert Einstein, although rejecting an ether medium for light, accepts both the theories of space and time contraction and dilation of Fitzgerald and Lorentz as valid in both of his famous two theories of relativity, the special theory and the general theory. In 1897, British physicist J.J. Thomson at Cambridge concluded that cathode rays are made of particles, later called electrons. This is the first particle, besides light, known to be smaller than an atom. The rise of the field of particle physics may also go on to indirectly contribute to a particulate view of light. The story of light gets, if you can imagine, even more nebulous in the 20th century, lost in a cloud of theoretical math, corrupted single-minded authority, and completely separated from physical reality. One problem is that this history is not widely publicized, taught, explained, and tested as a basis of fundamental education, so trying to understand this history clearly is difficult. In the year 1900, German theoretical physicist Max Planck publishes his famous paper that initiates so-called quantum theory, the theory that all energy exists in discrete energy elements. Planck also describes his famous equation E equals hv. Energy equals the Planck constant times the frequency of light. Planck found that this equation better fits so-called black body radiation, the way that all objects as they are heated seem to emit progressively higher frequencies of light. It is interesting to note that fluorescent materials, those substances that emit various frequencies of light after absorbing light, do not fit this model. But this view that energy seems to be made of particles somewhat helped to grow the rebirth of a corpuscular model for light started by the Michelson experiment. In 1903, Japanese physicist Hantaro Nagaoka put forward the Saturnian model of the atom. In this view, the atom is made of negatively charged electrons that rotate around a large mass positively charged particle, similar to how moons rotate around planets and planets rotate around stars. New Zealand physicist Ernest Rutherford will support this Saturnian model for the atom in 1911 after finding that the vast majority of alpha particles pass through materials without being reflected or deflected. I personally think that we should not rule out a so-called static model of the atom, where an atom is more like a typical star, planet, molecule, or mineral, etc. Perhaps an atom, like these materials, absorbs light into its many complex maze-like tunnels, which transfers motion into them, heating them up, and emit light which releases motion from them, cooling them down. Emitted light finally making its way to escape the many tunnels and latticework inside an atom. In 1905, Albert Einstein will use Planck's quantum theory to explain the photoelectric effect, the way that light can cause electric current to flow in some materials, where an increase in the frequency of light increases the amount of electricity produced, not an increase in light intensity. And this further revives a corpuscular theory for light. Einstein will also introduce his universal theories of relativity starting in 1905, removing the need for an ether medium for light as, quote, superfluous, while still seemingly maintaining Maxwell's double transverse light wave and accepting as true Fitzgerald's and Lorentz's space and time bending theories, leaving humanity with a double transverse light wave but no medium to transmit the wave, while space and time themselves compress and dilate in direct relation to the motion of matter moving through them in order to accommodate that motion to the speed of light, which is thought to always be constant. Experiments were later done to try and prove the theory that time changes for objects depending on their speed relative to an observer. In 1963, Frisch and Smith performed an experiment to demonstrate the relativistic time dilation effect on M mesons, originally named mesotrons, because they are subatomic particles with masses between the mass of a proton and the mass of an electron. Frisch and Smith measured the number of M mesons with velocity near the speed of light at the top of Mount Washington in New Hampshire, and then measured the number of high-speed M mesons at sea level in Cambridge, Massachusetts. They found that the half-life of M mesons was apparently increased because more high-speed M mesons reached the detector at sea level in Massachusetts than would be expected if the half-life of M mesons was that measured when these particles are at rest. However, this experiment appears to presume that the rate of M mesons that reach the Earth is constant. Otherwise, how could they be sure that they simply are not getting a larger quantity of M mesons at the time they happen to be counting the number of M mesons at sea level? Plus, what happened to the theory of George Fitzgerald's space contraction? By 1963, apparently there was only talk about time dilation, and no more talk about the theory of space contraction. Perhaps the view is that the space contracting for a high-speed M meson would be the cause of the M meson having a shorter travel time and apparent longer half-life. In that view, time dilation is the natural result of space contraction. Aside from the potential problems with this experiment, I think there could be other explanations for why M mesons might appear to have a longer half-life at high speed, including the theory that higher acceleration, which is required for objects to reach high speeds, forces higher pressures on the components of objects, perhaps helping to hold these components more firmly together for longer than objects not subjected to those accelerations. In 1971, Heffel and Keating performed an experiment to test if time appears to change in cesium beam atomic clocks on airplanes that are moving faster than stationary atomic clocks on the surface of the Earth. They did report measuring an apparent time dilation effect that was a change in the measured time of around 200 nanoseconds, an incredibly small amount of time. This did not completely agree with the theoretical value, but was relatively close. But as a thought experiment, imagine putting a mechanical clock in a stream of water. The water may cause the gears and hands of the clock to move more slowly, but that does not mean that time itself is moving more slowly. The same is true for atomic clocks. If a relative motion has an effect that delays the motion of light particles in an atom, that does not necessarily mean that time in the universe has slowed down, or that time for that particular atom has slowed down. For example, objects heated up exhibit different characteristics than they do at lower temperatures and pressures, but those changes are generally not thought to be connected to changes in the aging of the objects. For example, one avocado kept at room temperature may appear to age more quickly than another avocado kept in a refrigerator, which seems to retain its youthful unripeness longer. But that does not mean that the avocados are not aging at the same rate. It just means that their mechanical processes are moving at different rates. They are still aging at the same rate. Similarly, a mechanical clock that moves more slowly as a result of increased pull from some external force may not necessarily imply that time in the universe itself, or that time for that clock, has slowed down, but simply that particles in that field move more slowly because of increased collisions or physical barriers. In addition, those changes would only be in the specific direction of the motion, so seem to not be a universal omnidirectional phenomenon. The claim that time in the universe slows down or speeds up, depending on the relative motion of a piece of matter, is so speculative a claim that I think such a theory requires an effort to thoroughly explore alternative explanations. Beyond that, given government-supported theories like the single-shooter theory for the JFK and RFK murders, and the NIST explanation for how the WTC Building 7 collapsed, I think that we are certainly justified in maintaining doubts and skepticism about the honesty and accuracy of all scientific theories in this time. Einstein felt that we cannot simply add the velocity of a moving object to the velocity of light reflecting off of it or emitting from it. For example, the thought is that if we could add the velocity of an object moving toward us to the velocity of the light that is reflected off of the object, we would see objects moving toward us sooner than we would see objects that are not moving toward us, which is not the case. And therefore Einstein concluded that the speed of light must be constant, and beyond the speed of light being constant, that the speed of light can be used as a faithful measuring stick by which all other quantities and motions can be measured. In this view, the universe must always accommodate the speed of light. However, there are some phenomena that potentially disprove the theory that the speed of light is constant. For example, in 1960, Pound and Rebka, in addition to Crenshaw et al., had shown that the speed of light is not constant and is changed by the force of gravity. In 1911, Einstein had recognized that gravity would have an influence on light, which suggests to me that Einstein sided more with a corpuscular view of light. The provocative title of Pound and Rebka's paper, Apparent Weight of Photons, also suggests to me that they were making an effort to support the theory that light is made of material particles that have a definite mass. Another example of how the speed of light appears to not always be constant is when we observe light reflecting off of surfaces. In such occurrences, it cannot be dismissed that particles of light come to a complete stop for an instant when they reflect. One alternative theory being that light particles perform a 180-degree rotation without slowing down and without coming to a complete stop, like a comet orbiting a star does, which in my mind seems less likely. Even in the view of light as a wave, if light is a motion through a material medium, the motion would need to stop and be reversed at some point as well, making the speed of that motion not constant. In addition, Foucault had shown that the speed of light is slower in water than in air, although that can be attributed to delay as a result of particle collision in the case of the corpuscular theory, the collision of light particles with material in the water which diverts and delays the light particles. Or similarly, in the view of an undulatory theory, the light motion is delayed because of the collision of light medium particles with the other matter of the water that change the direction and therefore delay the motion of the light. Another potential problem arises when we imagine if we can add the velocity of some object to the velocity of light. Take, for example, a fast-moving object on Earth, like a car moving toward us at 100 kilometers per hour, that is 62 miles per hour. And light from behind us reflects off of the front of that car and then travels directly back to our eyes. Light travels around 300 million meters per second, so if we do add the speed of the car to the speed of light, how much sooner would we see that light reflected off the car, as opposed to light reflected from the non-moving objects around the car? So in terms of meters per second, the car is moving 100,000 kilometers per hour. Dividing that by 3,600 seconds equals 28 meters per second. So if we add that 28 meters per second to the 300 million meters per second speed of light, that is 300 million and 28 meters per second. If we were 1 kilometer away, just over half a mile away, how much sooner would the light arrive with that extra 28 meters per second added by the car? At the regular speed of light, without adding the motion of the car, the light arrives in 1,000 meters divided by 3 times 10 to the power 8 meters per second, and that's 3.333333 microseconds. But with this additional velocity, the light arrives in 1,000 meters divided by 300 million and 28 meters per second, which is 3.33333302 microseconds. That is 0.3 picoseconds. The light would arrive 0.3 picoseconds earlier, which I think would be very, very difficult to measure even in a precise experimental setting. Even with an extremely fast-moving or rotating object at a very large distance, trying to measure some difference in the speed of light reflecting off of an object with even a very high velocity would be very difficult because of the extremely high speed of light. In the case where light is emitted from a moving object, for example a car, perhaps light particles within the car maintain their own motion relative to any point in an absolute and unchanging space. And so, when light particles find an exit from the maze of matter in the car, they simply maintain that velocity, the same velocity they had bouncing around in the maze of matter within the car. Think about one person being on a roller coaster and another person being on the ground next to the roller coaster. Any velocity the roller coaster rider has is the same velocity the person on the ground has relative to the roller coaster rider, but in the opposite direction. When the roller coaster car accelerates, the person on the ride feels that acceleration, while the person on the ground does not feel that acceleration, even though their motions can be measured relative to each other. So that implies to me that motion, in this case acceleration, is relative only to absolute space. It only affects a body moving relative to its own position in absolute space, and does not depend at all on the position of the observer. In other words, the person on the ground can be thought to have the same motion in the opposite direction relative to the person on the ride, but in reality, that motion only is felt by the person on the ride, because motion appears to be relative to absolute space, not just to an observer. Over the course of the last 2 centuries, since the collapse of the corpuscular theory for light, people have been slowly putting forward corpuscular explanations for various observed phenomena of light. Prior to 1912, there was not really an acceptable corpuscular explanation of the dispersion of light into a spectrum of increasing distinct frequencies of light from a so-called diffraction grating, or prism, until William Lawrence Bragg's explanation of 1912, in which he explains that particles of light can reflect off regularly spaced rows of atoms in materials such as glass or off regularly spaced grating grooves, to produce a spread-out spectrum of regularly increasing frequencies of light. In 1913, Danish physicist Niels Bohr publishes his model of the atom, Electrons move in fixed circular orbits around a stationary positive nucleus with momentum h divided by 2 pi. H is Planck's constant. The electrons give off or absorb fixed amounts of energy, quanta, by moving from one orbit to another. Bohr's quantum theory for electrons and atoms is sometimes called the old quantum theory. One potential problem with Bohr's theory, and possibly with the Saturnian model for the atom in general, I think, is that in a typical hydrogen and oxygen gas combustion, where large quantities of light exit the reaction, it is difficult to believe that there are no atoms that are completely disintegrated. That is, that all the light, including heat, emitted from a typical hydrogen-oxygen combustion reaction results from electrons changing orbits, while all the hydrogen and oxygen atoms remain intact. Perhaps experiments comparing mass before and after combustion would show that far too much mass is missing to be accounted for only by electrons changing orbit, and some of that missing mass must be the result of protons and electrons that simply disintegrated into the light particles they are composed of. In 1922, U.S. physicist Arthur Compton publishes what will be called the Compton effect, the finding that X-rays are found to have a lower frequency after being reflected by graphite, which implies that light has momentum that is lost to an electron from the collision. This implies that light is made of material particles, since they appear to exhibit the property of having momentum. In 1923, Louis de Broglie calculated the mass of a light particle, or atom of light, to be less than 10 times 10 to the minus 50 grams. Much of quantum mechanics developed in only 3 years, from 1925 to 1928. In these years, Werner Heisenberg, with Max Born and Pascual Jordan, developed the use of matrices to describe mechanical motion, so-called matrix mechanics. This is the first version of quantum mechanics. In this time, the shift of focus moved from understanding electron motion within Saturnian model atoms to developing a math that could accurately describe the observable spectral lines emitted and absorbed by atoms and molecules. Also in these years, Erwin Schrödinger invented wave mechanics, a second form of quantum mechanics, in which a wave function is used to describe the state of a system. Matrix mechanics and wave mechanics were shown to be equivalent. Paul Dirac developed a relativistic wave equation for the electron, predicted so-called antimatter, and laid the foundations of quantum field theory by providing a quantum description of the electromagnetic field. In 1927, Arthur Compton will suggest the name photon for the light quantum. Finally, in these years, Bohr announces the complementarity principle, promoting the heartwarming theory of wave and particle theory equivalence. By 1928, the foundations of quantum mechanics were essentially complete. The current quantum view of light, where wave functions describe the probability of where matter might be located, has seemingly done away with any kind of mechanical view of light. What arose from the quantum theory of Planck and later scientists has been what seems like a great compromise between those who support a corpuscular theory for light and those who support a wave theory for light. And so now it is really a tie ball game where everyone wins except the truth, but at least everyone is happy. However, despite this kumbaya atmosphere where both theories are viewed as correct, in practice, a corpuscular theory for light is uniformly rejected by mainstream educators. One interesting aspect of the nearly extinct corpuscular theory for light is that perhaps the lambda symbol for wavelength could be represented by the Greek letter iota to represent the spatial interval between light particles in a beam of light, which is the equivalent of the letter lambda for the wavelength. And another letter could be used to represent the time interval of light particles, that is, the period between light particles in a beam of light. Another interesting part of the story about the human understanding of light is that many of these helpful and talented light theorists seem to be somewhat apparently conflicted in their views. In Le Monde, Descartes mostly appears to support a wave theory for light, however he clearly leaves the door open for a corpuscular theory. For much of the book Optics by Newton, Newton appears to accept the existence of an ether medium. It is only in the last few queries of his second edition, much later in 1718, that Newton suggests that we should dismiss the theory of an ether medium for light. However, even then he does appear to accept an ether medium, although in his view, light particles move through any medium and are not a motion that depends on a medium. Albert Michelson, who famously in 1881 published evidence against the existence of an ether medium, with the exception of an ether that moves along with the Earth, seemed to be supporting a corpuscular theory for light, even in 1927 openly rejecting the save the ethers theory of space, matter, and time contraction and dilation of Fitzgerald and Lorentz. But nonetheless, Michelson clearly advocates for the existence of an ether throughout that same work. Similarly, Einstein, in expanding on Planck's quantum view and 1905 rejection of an ether medium for light, seems to be supporting a corpuscular view of light, but at the same time includes and accepts as true the ether-saving theories of space, matter, and time contraction and dilation of Fitzgerald and Lorentz. So, in these characters, there seems in my mind to be some conflicting views between a corpuscular or undulatory theory for light. Perhaps some of this might be due to peer pressures, societal pressures, or simply not being able to clearly enunciate a simple singular universal theory. Even as long as this video is, I feel that there is much more to this story to reveal. I feel like I am just scratching the surface, and in addition, it seems to me that it is very possible that there are many important truths that are known but not yet revealed to the public. Like much of history, the story of human understanding of light is tough to grapple with in totality because there simply is a ton of data and history to examine, and I think many more experiments to perform. It is very difficult to get the full picture, but we should never stop trying to understand, learn, openly discuss, and teach these theories and this history, and to expand our understanding of light and the universe. Currently, the corpuscular theory is not totally extinct, although the transverse wave theory is much more dominant. So, although it is commonly acknowledged that a corpuscular or particle theory for light shares an equivalent status to the transverse wave theory, in practice there is no public discussion of light being made of material particles. Simply look at the Encyclopedia Britannica and Wikipedia entry for light. They describe light as electromagnetic radiation, which is based on the theory created by James Clerk Maxwell in 1864, who theorized that light is composed of two transverse sine waves conveyed by a medium, one being electric, the other being magnetic. Light can be emitted from electricity, but light can also be emitted by chemical reactions, mechanical, and other reactions. So light, in my humble view, seems to be merely a component of, and completely independent of, electromagnetism. Yet another potential problem with the theory that light is an electromagnetic wave is that light as a free-moving phenomenon does not appear to exhibit any electric or magnetic effect. The Encyclopedia Britannica and Wikipedia, and no doubt the keepers of the mainstream view, seem to mix together various historical theories of light. For example, they clearly define light as electromagnetic, accepting the famous theory of James Clerk Maxwell, but make no mention of light being, as Maxwell had defined light, a dual transverse wave being conveyed by a material medium. So Encyclopedia Britannica and other so-called authoritative sources support the theory of light being electromagnetic as Maxwell had defined it, but they cannot mention any material medium for that electromagnetic wave, perhaps because that would imply that they doubt the theories of relativity, in which Einstein clearly declared the need for an ether medium for light as, quote, superfluous. They seem to mix the theory that light is an electromagnetic wave with the more modern theory that light can be both a wave and a particle. However, again, for the wave portion of the theory, there is no mention at all of any kind of material medium for the light waves. One interesting aspect of our understanding of light is that, unlike molecules of air, the medium for sound on Earth, there has never been a way to make a vacuum that does not include light. That is, a container that does not allow some either light particles or light medium particles to exist within the container walls. We can evacuate containers to contain so little air that sound cannot be transmitted within them. However, there is no such vacuum that restricts either light particles, the corpuscular view, or light medium particles, the undulatory view. In fact, that is, I think, another possible problem with a wave theory for light. It seems likely that if there was a medium for light, that there might naturally occur, as is the case for the air molecule medium for sound around the Earth, spaces where the medium for light is patchy or not complete, and therefore does not allow light to pass through it. But we, apparently, have never encountered any such areas in space where light has had trouble being transmitted because of an incomplete material medium. Light, in my opinion, most likely exists as small material particles that form the basis of all matter in the universe. For Encyclopedia Britannica and Wikipedia, light is talked about in terms of wavelength only and not particle interval, and is viewed primarily in terms of quantum physics as consisting of discrete packets of, quote, energy, called, quote, photons. So currently, an energy-based theory of light dominates human thinking. However, the concept of energy is a product of mass and motion. It is a combination of mass and motion into one quantity. And so one could argue that mass and motion, while both always independently conserved, can never convert into each other, matter into motion and motion into matter. And so this explanation for light, in my mind, seems only temporary, being too high level, and not reduced to individual primary components. This modern quantum view of light sadly has separated light from any kind of mechanical reality that might have existed in the 1800s so-called classical two famous competing views of light. The corpuscular, where light is made of material particles like fundamental atoms that move independently of any material particle medium, or the undulatory, where light is viewed as a motion that depends exclusively on a material particle medium. The Encyclopedia Britannica summarizes this nebulous, modern, compromised quantum view well, stating, "Neither a classical wave model nor a classical particle model correctly describes light. Light has a dual nature that is revealed only in quantum mechanics. This surprising wave-particle duality is shared by all of the primary constituents of nature. For example, electrons have both particle-like and wave-like aspects. So in this view, not only light, but electrons, and presumably all primary constituents of nature, have this dual nature where they cannot be described accurately as physical objects anymore." Perhaps accepting highly speculative generalizations as absolute certain truth with absolutely no room for possible alternatives is more comforting than accepting that, for now at least, there is no easy way to precisely predict all of the motions of matter in a universe made of millions of particles and particle collisions. Unfortunately, it seems likely that this 200 and counting year detour away from Descartes and Newton's simple theory that light is made of tiny material particles that do not depend on a material medium is going to continue for many more years, perhaps even for a few more, gasp, centuries, until the clear and simple truth about light is exposed by fully flushing out the true nature of light and by making that truth extremely clear to all the people of planet Earth.